One molecule smells like mint. Its mirror image smells like caraway seeds. Chemically, they're almost identical. They contain the same atoms, the same bonds, and the same molecular formula. Yet somehow your brain perceives them as completely different smells. Watch until the end of the video to find out why. But first, we need to understand how smell works. When molecules evaporate into the air, they enter the nose and dissolve into a layer of mucus inside the olfactory epithelium. From there, they bind to specialized olfactory receptors on sensory neurons. These neurons generate electrical signals which are sent to the brain, where they are interpreted as smell. The smell of a molecule depends on three main things: how easily it evaporates, how well it dissolves in mucus, and how it interacts with olfactory receptors. One important factor is molecular size. As molecules become larger, London dispersion forces become stronger, making them less volatile and therefore less likely to evaporate. On the other hand, very small molecules may not interact strongly enough with receptors. Molecular size also affects the shape of the molecule, changing how it fits into receptor binding sites. Polarity is equally important. Molecules need to be polar enough to dissolve in the mucus lining the nose, but if they are too polar, strong intermolecular forces make them less volatile. Many molecules therefore occupy a balance between volatility and solubility. Functional groups also influence smell. Esters often have fruity or sweet aromas. For example, isoamyl acetate smells like banana, ethyl butanoate resembles pineapple, methyl butanoate is often described as apple-like, and octyl acetate has an orange aroma. Aldehydes tend to produce fresher smells. Hexanol contributes to the scent of freshly cut grass. Benzaldehyde smells like almonds or cherries, and cinnamaldehyde gives cinnamon its characteristic aroma. Ketones are often sweet, floral, or minty. Carvone itself is a ketone, while ionones contribute violet-like floral notes. In contrast, almonds and sulfur-containing thiols are frequently associated with fishy, rotten, or unpleasant smells. Despite having only around 400 types of olfactory receptors, humans can distinguish millions of different smells. This is because each molecule activates a unique combination of receptors. Rather than one receptor corresponding to one smell, the brain interprets patterns of receptor activity. It's similar to how just 3 color receptors in the eye allow us to perceive millions of colors. This brings us back to Carvone. Carvone exists as 2 enantiomers, non-superimposable mirror images, much like your left and right hands. Although they contain the same atoms and bonds, their 3-dimensional arrangements differ. Since olfactory receptors are proteins and proteins are themselves chiral, each enantiomer interacts differently with the receptor binding site. As a result, they trigger different patterns of neural activity and are perceived as different smells. The same phenomenon occurs with limonene, where one enantiomer is associated with oranges and the other with pine-like aromas. Thank you for watching. Like and subscribe if you want to see more.